Hey everyone, welcome to this video about half-life. This is one of the big applications of nuclear chemistry. So you just watched a video about nuclear chemistry, which is basically referring to radiation or radioactive elements. And when something is radioactive, its nucleus is unstable and it will emit either a particle or a wave. And so what we can do is we can actually apply that to our knowledge of how certain radioactive elements will decay over time. So let's take a look. A half-life is the time that it takes for one half of a sample to decay. And when we're solving half-life problems, we will use the method of making a table. We'll draw a table that has time and amount, and we'll put a 0 at the top of the time column. Then we'll count up by however long the half-life is. Next, we'll put the mass that you start with at the top of the amount column, and then we'll divide the initial mass in half for each row as you go down the table. Now, do you think chemists usually make a chart or a table when they're calculating half-life? What if we're talking about 100 half-lives later? Are they going to make a table with 100 half-lives? Well, the answer is no. But for the purpose of general chemistry, you can do all the problems that I would give you by using a table. If you were to go on and pursue chemistry as a career pathway, you might end up working with half-lives and radioactive materials. And so you would eventually learn how to use the formula that's shown here. But it's kind of a complex formula, and you could go ahead and figure it out if you wanted to understand how to use it. It's a little bit advanced for what we are covering here, but just know that you can do everything by using the table method. So let's see an example. Here's a half-life problem. The half-life of substance A is 10 minutes. Initially, we have 256 grams of substance A. How much of substance A is left after 4 half-lives? And I've already solved it out for you by using the table, so you can take a look at this. But here's how you would do it. You might make an extra column that says the number of half-lives, since we're talking about how much is left after a certain number of half-lives. Then you can put time. Remember, you're going to start with 0 at the top of the time column and then count up by however long the half-life is. Since our half-life was 10 minutes, we counted up 0, 10, 20, 30, 40, 50, and 60. In the last column, we put amount, and I put amount remaining in grams, since we know we started with 256 grams based on this question. So 256 divided by 2, because remember, you're going to divide it in half each row as you go down the table. 256 divided by 2 is 128. Divide that by 2 is 64. Divide that by 2 is 32. Then 16, 8, and 4. And if we're using this table method, we can tell pretty easily that there will be, after 4 half-lives, 40 minutes has gone by and there are 16 grams of substance A remaining. So if you really wanted to, and if you're a more visual person, you could chart this in this line graph. So what's happening is we have on the x-axis the amount of time, and on the y-axis the concentration of substance A, or the amount of substance A. And what you can see is that for every 10-minute period, which is the half-life of substance A, you're decreasing your amount by half. And so it quickly gets smaller and smaller and smaller amounts, and it'll keep getting smaller and smaller and smaller and smaller and smaller until you're basically left with 2 atoms, and then it'll divide in half and you'll have 1 atom left, and then that's kind of it. Once that atom would decay, then that's all that's left of that sample, and you would no longer have that element anymore. So kind of interesting. Thanks so much for listening to our problem about half-life and learning this application of nuclear chemistry.